The cold hit different at 9,000 feet. One trapper learned that his first winter in the South Fork of the Platte Basin in 1883, when his cabin floor dropped to 5 degrees Fahrenheit and frost formed on his blankets 3 feet from the stove. He had built exactly the way every mountain man was told: tight log walls, cast iron stove, keep the fire burning overnight, standard and trusted. By winter's end, he had burned more wood than 2 men should need, and still woke to freezing air. Across the high country, trappers fought the same losing battle in cabins built by the book. Over 3 winters, he quietly applied an older method that kept his shelter 39 degrees warmer all night while neighbors still froze. What did he understand about heat storage that every mountain builder should know? Thomas Gray had arrived in the South Fork Valley that October, after a month working trap lines further north, carrying the standard wisdom every experienced mountain man swore by. The logic seemed bulletproof: stack 3 cords of seasoned pine before the snow flies, chink the gaps tight with mud and moss, keep that cast iron stove fed through the night, and you would survive whatever the Rockies threw at you. The army posts recommended it, the territorial handbooks preached it, and every supply catalog from Denver to Cheyenne sold the equipment to make it work. Cast iron stoves were reliable, logs grew thick in the surrounding forest, and hauling in elaborate insulation materials would cost more than most trappers earned in a season. Gray had followed those instructions to the letter when he raised his cabin walls in late September. He selected tight-fitting lodgepole pine logs, sealed every visible gap with clay-rich mud from the creek bottom, and positioned his stove dead center, where the heat could reach every corner. He had even splurged on a damper system for the stovepipe, convinced that controlled airflow would make his fuel last longer. By the time the first heavy snows locked him in for the winter, he had 4 full cords split and stacked under cover, enough wood to outlast any cold snap the high country could deliver. The first test came on a November night when the temperature outside plummeted to 20 below zero Fahrenheit. Gray loaded his stove at 10 in the evening with enough split pine to burn until dawn, confident in the system that had kept countless frontiersmen alive. He woke at 4 in the morning to find the fire reduced to glowing embers, and the cabin interior transformed into something resembling a root cellar. The rough-hewn plank floor next to his sleeping platform had dropped to 5 degrees Fahrenheit, cold enough that the water bucket had developed a skin of ice despite sitting only 3 feet from the stove. Frost had formed on the inside surface of his blanket, where his breath condensed and froze during the night. Gray rekindled the fire and spent the rest of that week burning through wood at a pace that alarmed him. 3 full cords disappeared in 7 days, yet the floor temperature never climbed above 15 degrees Fahrenheit, even with the stove roaring. The cast iron heated the air directly above it, but that warmth rose to the ceiling and escaped through gaps in the roof construction, leaving the sleeping level perpetually cold. Worse, condensation from the warm air meeting cold log surfaces created ice buildup on the interior walls, making the cabin feel like the inside of a cave. 2 neighboring cabins in the same drainage suffered identical problems that winter. One trapper abandoned his shelter entirely by January after ice formation on the interior logs made the structure unsafe, retreating to a line shack 15 miles downstream. Another burned through 5 full cords in 6 weeks and still recorded interior temperatures of only 12 degrees Fahrenheit during a stretch when outside readings hit 20 below. The standard method that worked reliably at lower elevations and milder climates simply could not overcome the heat loss at 9,000 feet elevation with sustained sub-zero temperatures and wind exposure. Gray brought unusual qualifications to this problem. His father had immigrated from the Sogn district of Norway in the 1850s, carrying with him the building traditions of Scandinavian farmsteads, where winters stretched 6 months and fuel conservation meant survival. During boyhood summers back east, Gray had helped construct sleeping benches with stone underlays and watched his father build massive thermal mass hearths that radiated heat through the night after the fire died down. The old man had explained how Norwegian builders understood that continuous burning wasted fuel, while stored heat in stone and earth provided steady warmth with less wood consumption. Gray also carried knowledge from 3 seasons working the trade routes near Shoshone winter camps, where he had observed indigenous builders constructing elevated sleeping platforms with carefully arranged rock masses underneath. The Shoshone method involved heating stones in a separate fire, then transferring them to pits beneath raised sleeping areas where they radiated warmth upward through layers of pine needles and buffalo hide. He had watched families sleep comfortably through sub-zero nights using this thermal storage approach, while burning far less fuel than the typical frontier cabin required. When Gray began discussing alternative heating methods with his neighbors and the local supply foreman, he encountered immediate resistance. James McAllister, who managed trapline logistics for the region, shook his head when Gray mentioned hauling heavy metal containers for heat storage. McAllister had supervised remote camp construction for 5 seasons and trusted the proven handbook approach that emphasized continuous burning over complex thermal systems. He told Gray that mountain men needed simple, reliable methods, not elaborate, contraptions better suited to city folks with time and money to spare. The other trappers in the drainage echoed this skepticism, calling Gray's ideas unnecessarily complicated when the real solution was simply cutting more wood and keeping better fires. This social pressure reinforced the conventional wisdom that dominated frontier heating practices throughout the Rocky Mountain territories. The territorial government published standard cabin construction guidelines that recommended wood stove heating as the safest and most practical approach for isolated settlements. Supply companies marketed their cast iron stoves with promises of reliable warmth and fuel efficiency, while the alternative heating methods Gray had observed among indigenous communities were dismissed as primitive techniques unsuitable for civilized construction. Yet Gray could not ignore the evidence accumulating around him. The standard stove method produced comfort levels that barely qualified as survival, consumed enormous quantities of fuel, and required constant attention throughout the night to prevent dangerous temperature drops. He began that winter with conventional expectations, but ended it convinced that the accepted wisdom contained fundamental flaws. The gap between promised performance and actual results demanded investigation, and Gray possessed the cultural knowledge to pursue alternatives that his neighbors had never seriously considered. The question was whether traditional thermal storage methods could be adapted to log cabin construction at high altitude, and whether the social resistance to change could be overcome by demonstrated results. Gray spent the spring of 1884 analyzing the fundamental flaw in standard cabin floor construction. The problem lay not in the stove itself, but in the direct thermal bridge between the sleeping area and the frozen ground beneath. Traditional cabin builders laid rough-hewn planks directly over log skids, creating minimal separation between the sleeper and the earth that remained frozen solid from November through April at 9,000 feet elevation. Heat from the stove warmed the air above the floor, but that warmth immediately conducted downward through the wooden planks into the frozen substrate, creating a continuous drain on any heat the cabin managed to accumulate. During a summer visit to the Norse immigrant settlement 30 miles downstream, Gray studied the construction methods that Olaf Hansen had brought from the Son district. Hansen's workshop contained a traditional Scandinavian sleeping bench, elevated 18 inches above the main floor on heavy timber supports, with carefully arranged stone masses beneath the sleeping surface. Hansen explained that Norwegian builders understood the principle of thermal separation. By creating an air gap between the sleeper and the frozen ground, then filling that gap with materials that stored rather than conducted heat, the sleeping area could maintain warmth even after the main fire died down. Gray also recalled the elevated platforms he had observed in Shoshone winter lodges during his trading seasons. Nisa Many Paths, an elder known for her lodge construction expertise, had shown him how her people built raised sleeping areas using a foundation of carefully selected stones arranged beneath layers of pine needles, buffalo hide, and woven grass mats. The stones absorbed heat from fires built during the evening, then radiated that warmth upward through the night, while the insulating materials prevented rapid heat loss to the surrounding earth. When Gray began construction of his modified platform system that fall, he started by removing the existing floor planks in the sleeping area of his cabin and excavating 18 inches into the earth beneath. He cut heavy lodgepole pine timbers to serve as the platform frame, creating a rectangular sleeping area 6 feet by 8 feet elevated above the excavated cavity. The timber frame provided structural support while creating the crucial air gap that would break the thermal bridge to the frozen ground. The foundation layer required careful material selection. Gray hauled coarse gravel from a creek bed 2 miles distant, sorting pieces that ranged from walnut size to chicken egg dimensions. He compacted this gravel into a 6-inch base layer that would provide drainage and prevent frost heaving while creating thermal mass beneath the platform. Over the gravel, he spread a 2-inch layer of fine sand mixed with clay-rich soil that would conform to the gravel surface and provide a stable base for the stone layer above. The critical component was the flat stone layer that would serve as the primary thermal mass. Gray selected slate pieces from an exposed outcrop a day's travel up the valley, choosing slabs roughly 12 inches square and 2 inches thick. He arranged these stones in an overlapping pattern across the sand layer, creating a continuous thermal mass that could absorb and store heat from above while preventing cold air movement from below. The spaces between stones were packed with smaller slate fragments to eliminate air gaps. Around the perimeter of the excavated area, Gray installed a skirt wall system that would prevent cold air infiltration beneath the platform. He cut short sections of lodgepole pine and drove them vertically into the earth around the platform edges, creating a barrier that extended from the stone layer to the platform frame above. The gaps between these vertical logs were tightly packed with moss gathered from north-facing slopes, pine needles collected from the forest floor, and clay-rich mud that would harden and seal against air movement. The insulation system above the stone mass combined materials adapted from both Norwegian and indigenous traditions. Gray spread a 4-inch layer of wood ash mixed with fine sawdust over the slate stones, creating an insulating blanket that would prevent rapid heat loss upward while allowing gradual warming of the thermal mass. Over this insulation layer, he laid heavy sheepskin rugs obtained through trade, topped with a buffalo hide that provided additional insulation and a comfortable sleeping surface. Gray tested his completed platform system during a cold snap in early December when outside temperatures dropped to 15 degrees Fahrenheit below zero. He loaded his stove normally at 10 in the evening and allowed it to burn down to coals by midnight. At 2 in the morning, he measured the platform's surface temperature at 54 degrees Fahrenheit, while the cabin air temperature had fallen to 22 degrees Fahrenheit. The platform remained noticeably warmer than the surrounding air throughout the night, and Gray woke without the bone-deep cold that had plagued him the previous winter. The performance difference became more apparent when compared to neighboring cabins using standard floor construction. During the same cold snap, McAllister's cabin recorded a floor temperature of 8 degrees Fahrenheit and air temperature of 12 degrees Fahrenheit at the same 2 o'clock measurement time. The occupant reported waking multiple times to stoke the fire and experiencing frozen condensation on his blankets, while Gray slept through the night without disturbance. More significantly, the platform system reduced wood consumption by approximately 30% compared to standard heating methods. Gray found that his stove required only 1 reload around 10 in the evening, rather than the 2 or 3 reloadings necessary to maintain barely tolerable temperatures in conventional cabins. The thermal mass beneath the platform continued radiating stored heat upward through the night, maintaining sleeping area warmth without active fire. Gray's innovation demonstrated that effective cold weather shelter required understanding heat storage and thermal separation rather than simply burning more fuel. The elevated platform broke the direct connection between sleeping area and frozen ground, while the stone thermal mass absorbed heat during active burning and released it gradually through the night. The insulation layers prevented rapid heat loss, while the perimeter skirt walls eliminated the cold air infiltration that undermined heating efforts in standard construction. This integrated approach to envelope design represented a fundamental shift from the continuous fuel consumption model that dominated frontier heating practices, proving that traditional knowledge adapted to local conditions could outperform accepted wisdom. Despite the success of his elevated platform system, Gray discovered a critical limitation during the brutal cold of January 1885. Even with the stone thermal mass and insulation layers performing as designed, the platform's surface temperature still dropped from an evening high of 60 degrees Fahrenheit to a morning low of 32 degrees Fahrenheit when outside temperatures hit 5 degrees below zero. The slate stone simply could not store enough heat to maintain comfortable sleeping temperatures through 10 hours of sub-zero conditions without active fire. Gray recognized that he needed a thermal storage medium with significantly greater heat capacity than stone. During his childhood observations of Norwegian heating systems, he had watched his father prepare heated water containers for winter sleeping benches, explaining that water could hold nearly 4 times more heat per pound than equivalent masses of stone or metal. A gallon of water heated to near boiling would release the same amount of thermal energy as 4 gallons of heated stone while occupying far less space beneath the platform. The challenge lay in safely containing and positioning large volumes of heated water where they could transfer their stored energy to the sleeping area without creating structural problems or safety hazards. Gray began experimenting with container materials available through frontier supply networks, testing copper pots, cast iron vessels, and tin containers of various sizes. He discovered that thin-walled tin containers conducted heat more efficiently than thick cast iron, while being far less expensive than copper alternatives that required special ordering from Denver suppliers. Gray settled on a configuration using 2 large tin containers, each capable of holding 12 gallons of water and measuring approximately 24 inches long by 10 inches in diameter. These dimensions allowed the containers to fit within the excavated space beneath his platform while providing sufficient surface area for heat transfer to the surrounding thermal mass. He positioned the containers lengthwise on either side of the platform area space to distribute heat evenly across the entire sleeping surface. The installation required careful engineering to ensure proper heat distribution and container protection. Gray excavated additional space 12 inches beneath his existing stone layer, creating cavities that would accommodate the water containers while maintaining the structural integrity of the platform system above. He built wooden crate forms around each container cavity, lining them with additional flat stones to create thermal conduction pathways between the heated water and the surrounding gravel mass. The key innovation involved using the existing sand and gravel layers as a heat distribution medium. When the heated containers were buried within this mineral matrix, thermal energy transferred outward through conduction, warming the entire volume of material beneath the platform, rather than creating isolated hotspots. Gray packed additional sand around each container to ensure intimate contact between the metal surfaces and the heat distribution medium, eliminating air gaps that would impede thermal transfer. Gray developed an evening routine for charging his thermal storage system that integrated with his normal cabin maintenance schedule. Each evening around sunset, he filled both containers with water and heated them to approximately 210 degrees Fahrenheit using his existing wood stove. The heating process required roughly 45 minutes and consumed no additional fuel beyond his normal evening fire, since he simply utilized stove capacity that would otherwise heat only the cabin air. Installing the heated containers required a trapdoor access system cut into the platform decking. Gray designed hinged wooden panels that allowed him to lower the containers into their buried positions each evening, then secured the access panels to prevent heat loss upward. The system included simple rope and pulley arrangements that made handling the heavy water-filled containers manageable for one person operating alone. During a test period in February 1885, Gray documented the performance improvements achieved by combining water thermal storage with his existing platform insulation system. On a night when outside temperatures dropped to 0 degrees Fahrenheit, he measured platform surface temperatures of 73 degrees Fahrenheit at 2 o'clock in the morning and 58 degrees Fahrenheit at 6 o'clock the following morning. The cabin air temperature remained at 45 degrees Fahrenheit at the 2 o'clock measurement and 39 degrees Fahrenheit at dawn, representing a remarkable 39-degree difference between interior and exterior conditions. The thermal storage system eliminated the need for overnight fire maintenance that plagued standard heating methods. Gray's stove required no fuel additions between his 10 o'clock evening loading and his 8 o'clock morning restart, reducing wood consumption to less than 1 cord per week compared to the 3-cord weekly consumption typical of neighboring cabins using conventional heating approaches. An unexpected benefit involved humidity control within the cabin environment. The gradual release of thermal energy from the water containers reduced condensation formation on interior log surfaces by approximately 60% compared to the previous winter. The steady, even heat prevented the extreme temperature fluctuations that caused moisture in cabin air to condense and freeze on wall surfaces, keeping interior logs dry and preventing the ice buildup that had plagued his first winter using standard heating methods. Gray encountered technical challenges that required system refinements during the extreme cold of late February. A sudden temperature drop to 30 degrees below zero Fahrenheit caused condensation problems within one of the containers, leading to a small leak that allowed heated water to seep into the surrounding sand layer. He discovered that the rapid temperature differential between the heated container and the frozen surrounding materials created thermal stress that the thin tin construction could not reliably withstand. The solution involved upgrading to heavier gauge tin containers and implementing a cushioning system using additional sand layers around each container. Gray also added small vent holes near the top of each container to allow thermal expansion without creating destructive pressure buildup. These modifications required replacing his original containers, but eliminated the leakage problems and allowed reliable operation through the remainder of that severe winter. Gray's water thermal storage innovation demonstrated the principle of heat capacity optimization in frontier heating systems. By selecting a storage medium with superior thermal properties and integrating it with his existing platform insulation design, he created a heating system that maintained comfortable sleeping temperatures through extended periods without active fire, while consuming far less fuel than conventional approaches. The success of this combined system established thermal storage as a practical alternative to continuous fuel consumption for high-altitude winter survival. Gray discovered during the winter of 1886 that his thermal storage system faced a new challenge that threatened to undermine its effectiveness. Despite the excellent performance of his water containers and platform insulation, sudden windstorms created unpredictable heat losses that could drain his stored thermal energy faster than the system could compensate. During a March blizzard with sustained winds of 25 miles per hour, Gray measured his platform surface dropping from 60 degrees Fahrenheit to 41 degrees Fahrenheit in just 4 hours, even though the buried containers remained fully charged with heated water. The problem lay in air infiltration pathways that the original platform design had not adequately addressed. High winds created pressure differentials around the cabin that forced cold exterior air through gaps beneath the raised platform, carrying away the thermal energy that should have remained trapped within the insulation layers. Gray observed that wind-driven air movement beneath his platform created convective cooling that overwhelmed the radiant heating from his water containers, essentially turning his thermal mass into a heat exchanger that warmed the passing cold air rather than maintaining the sleeping area temperature. Gray studied the air movement patterns around his cabin by observing smoke from small fires placed at various locations during different wind conditions. He discovered that prevailing westerly winds created positive pressure on the windward cabin wall, while generating negative pressure on the leeward side, establishing air currents that flowed directly beneath his elevated platform. These currents followed the path of least resistance through the gravel and sand layers surrounding his water containers, carrying away thermal energy that should have radiated upward to the sleeping surface. The solution required implementing adjustable airflow controls that could adapt to changing weather conditions while maintaining the thermal performance of the storage system. Gray designed a perimeter skirt system using 12-inch wide boards cut from split pine logs and hinged along the platform edge with leather strips. During severe wind conditions, he could close these skirts to create a sealed cavity beneath the platform, preventing cold air infiltration while trapping heated air around the thermal storage containers. The skirt panels incorporated additional insulation layers, using materials adapted from plateau tribal winter shelter techniques that Gray had observed during earlier trading seasons. He packed pine needle debris between double-board walls, creating insulation panels that could be adjusted seasonally while providing effective air sealing during extreme weather. The hinge design allowed the skirts to be opened during milder conditions to prevent moisture buildup and provide ventilation that would prevent condensation problems within the thermal storage cavity. Gray also recognized that his stovepipe system was creating excessive draft that pulled heated cabin air upward faster than his thermal storage could replace it. Standard Frontier stove installations used wide-open dampers to ensure adequate combustion air and prevent dangerous backdrafts, but this approach created continuous airflow that stripped heat from the cabin interior even when active fires were not burning. Gray installed an adjustable damper system in his stovepipe that allowed him to restrict airflow during overnight periods when the fire had burned down to coals. The damper control required careful balance to maintain safe operation while optimizing heat retention. Gray developed a technique for adjusting the damper opening based on exterior wind conditions and interior temperature measurements, gradually closing the damper as evening fires burned down while monitoring for any signs of combustion problems. He discovered that reducing the chimney draft by approximately 50% during overnight hours allowed his thermal storage system to maintain cabin temperatures without the continuous air exchange that had been stripping away stored heat. An additional innovation involved seasonal window modifications that allowed Gray to optimize solar heat gain during transitional periods when daytime temperatures climbed above freezing but nighttime conditions remained severe. Gray replaced his single-pane window with a double-layer oiled cloth system during the coldest months, reducing radiant heat loss through the glazing while maintaining adequate daylight for interior activities. During spring conditions when daytime solar heating became significant, he switched to single-layer glazing that allowed maximum solar energy collection while his thermal storage system handled nighttime heating requirements. The seasonal window system included removable insulation panels that Gray installed during extended cold periods to eliminate heat loss through the largest thermal weak point in his cabin envelope. These panels used buffalo hide stretched over wooden frames and filled with goose down obtained through trade, creating insulation values that significantly exceeded standard glazing, while maintaining the option to restore daylight and solar heat gain when conditions permitted. Gray tested his complete ventilation control system during a severe windstorm in late winter when exterior temperatures dropped to 10 degrees Fahrenheit with sustained winds gusting to 30 miles per hour. With his skirt panels closed and damper adjusted to half-open position, he measured platform temperatures of 56 degrees Fahrenheit at dawn compared to 41 degrees Fahrenheit recorded during the previous windstorm without airflow controls. The cabin air temperature remained at 37 degrees Fahrenheit compared to 28 degrees Fahrenheit achieved without ventilation management. The performance improvement became more dramatic when Gray compared his results to neighboring cabins that lacked airflow control systems. McAllister's cabin, using standard construction with open floor gaps and wide-open stove dampers, recorded interior air temperatures of 12 degrees Fahrenheit and floor temperatures of 8 degrees Fahrenheit during the same storm conditions. The occupant reported waking multiple times during the night as wind-driven drafts overwhelmed his heating system, despite continuous fuel consumption. Gray's ventilation innovations demonstrated that effective thermal storage required active management of air movement patterns rather than passive reliance on insulation alone. By controlling drafts beneath the platform and managing chimney-induced air exchange, he created a system that retained stored thermal energy even under severe weather conditions that defeated conventional heating approaches. The seasonal adaptability of his window and damper systems allowed optimization for changing conditions throughout the winter heating season, maximizing both solar heat gain and thermal retention as environmental conditions shifted. The integration of airflow control with thermal storage represented a fundamental advancement in frontier heating technology, proving that traditional indigenous and immigrant knowledge of air movement management could dramatically improve the performance of innovative thermal systems when properly adapted to high-altitude mountain conditions. The ultimate test of Gray's integrated heating system arrived during the winter of 1887, when an Arctic air mass settled over the Rocky Mountain high country and refused to move. For 8 consecutive nights, temperatures plummeted to an average of 20 degrees below 0 Fahrenheit, while sustained winds of 20 to 30 miles per hour created conditions that challenged every heating method in the South Fork Basin. This was the kind of weather that killed unprepared travelers and forced even experienced mountain men to make desperate decisions about fuel consumption and survival priorities. Gray's 3 neighboring cabins using conventional heating methods faced immediate crises as the cold snap intensified. The cabin closest to his own, occupied by a trapper named Morrison, followed standard frontier practice with a central cast iron stove and minimal floor insulation. On the first night of the cold snap, Morrison's cabin interior dropped from 12 degrees Fahrenheit at dusk to 8 degrees Fahrenheit by dawn, while his floor temperature measured 6 degrees Fahrenheit despite burning wood continuously through the night. Morrison consumed nearly 3/4 of a cord in that single night and woke to find frost formations on his interior log walls where condensation had frozen solid. McAllister's supply station cabin, built according to territorial handbook specifications, performed only marginally better during the extended freeze. His interior air temperatures ranged from 18 degrees Fahrenheit in the evening to 10 degrees Fahrenheit by morning, requiring constant fire tending and consuming 5 full cords over the 8-night period. McAllister reported that his sleeping area never warmed above freezing despite round-the-clock fuel consumption, and ice buildup on interior surfaces created dangerous structural stress on the log chinking. A third cabin in the drainage, occupied by 2 trappers using a larger stove and extra insulation materials, managed interior air temperatures of 25 degrees Fahrenheit at dusk, declining to 15 degrees Fahrenheit by dawn. Their floor remained at 12 degrees Fahrenheit throughout the cold snap, and they burned through 4 cords while still experiencing uncomfortable sleeping conditions that required multiple clothing layers and shared body heat for survival. Gray's thermal storage system performed dramatically differently under the same extreme conditions. On the coldest night, when exterior temperatures hit 25 degrees below 0 Fahrenheit with winds gusting to 35 miles per hour, Gray measured his platform surface at 60 degrees Fahrenheit at 2 o'clock in the morning and 52 degrees Fahrenheit at dawn. His cabin air temperature remained at 41 degrees Fahrenheit at the 2 o'clock measurement and 39 degrees Fahrenheit when he woke at 6 in the morning, representing a thermal difference of nearly 90 degrees Fahrenheit between his sleeping surface and the exterior conditions. The wood consumption comparison revealed the dramatic efficiency advantages of thermal storage over continuous burning approaches. Gray used exactly 1 cord of split pine over the entire 8-night period, loading his stove normally each evening and allowing it to burn down to coals by midnight without any overnight refueling. His water containers, charged to 210 degrees Fahrenheit each evening, provided sufficient thermal energy to maintain comfortable sleeping temperatures through 10 hours of sub-zero conditions with high wind loading. More significantly, Gray's system required no emergency interventions or survival compromises during the extreme weather. He slept undisturbed through each night without waking to tend fires, experienced no frost formation on blankets or interior surfaces, and maintained normal daily routines while his neighbors struggled with heating crises that threatened their safety. The consistent performance under maximum stress demonstrated that thermal storage systems could provide genuine comfort rather than mere survival under conditions that defeated conventional heating methods. The performance differences became impossible for neighboring trappers to ignore when Gray's cabin remained comfortable while others faced potential evacuation. Morrison visited Gray's cabin on the 4th night of the cold snap and immediately noticed the warm floor surface and absence of condensation on interior walls. When Gray demonstrated his water container loading routine and explained the thermal storage principles, Morrison asked detailed questions about container sizing, burial depth, and insulation requirements. McAllister arrived the following day with specific interest in Gray's wood consumption figures. When Gray showed him the remaining fuel from his winter supply and explained that he had burned only 1 cord during the worst weather of the season, McAllister requested permission to examine the platform construction and thermal storage installation. McAllister had been responsible for supplying emergency fuel deliveries to several cabins during the cold snap, and Gray's fuel efficiency offered obvious logistical advantages for remote camp operations. Word of Gray's heating innovation spread through the trapping network during the following summer when traders and trappers gathered at supply rendezvous points. Several experienced mountain men requested detailed explanations of the water container burial system and platform insulation methods, particularly after hearing quantified performance reports from the 1887 winter. Gray found himself teaching construction techniques to trappers, planning new cabin builds, and advising on modifications to existing structures. By the winter of 1889, 3 cabins in the immediate area had installed variations of Gray's thermal storage system. Evelyn Logan, who had claimed a homestead site 5 miles downstream, built a scaled-up version using 4 12-gallon containers beneath an enlarged sleeping platform designed for family use. Her installation maintained interior temperatures above 40 degrees Fahrenheit through severe cold snaps while consuming 60% less fuel than comparable homestead cabins using conventional heating. The territorial supply company that served the South Fork region included a brief mention of thermal storage heating in their 1890 winter preparation circular, describing Gray's innovation as a proven method for high-altitude cabin heating. The reference noted that several successful installations had demonstrated superior performance compared to standard stove heating, particularly regarding fuel efficiency and overnight temperature maintenance. Evidence of Gray's thermal storage innovation persisted in remote cabin construction well into the 20th century. Archaeological surveys of abandoned high-altitude cabins from the mining boom period revealed platform cutouts and container placement patterns consistent with buried thermal mass systems. Building techniques that incorporated water-filled containers beneath raised floors appeared in several homesteading guides published during the early 1900s, suggesting that Gray's methods influenced mainstream frontier construction practices. The fundamental principles Gray demonstrated through his integrated system proved that effective cold weather shelter required understanding thermal storage, air movement control, and insulation design rather than simply consuming more fuel to maintain barely tolerable conditions.